Yeah, you're
Hi,
closer.
students. We are talking about triangle congruence using a couple different methods today. Hi, students. We're talking about triangle congruence using a couple different methods today. It's good to see you.
Hello, friends.
All right. So the last thing that we looked at, we learned about showing that two triangles were exactly the same. And to do so, we had to show all three sides and all three angles were exactly the same. That's a lot. Uh,
That's
one of
like
the
6 things. Whew.
Yeah, that's like, whew, that is a lot of different things, six altogether. And one of the things that we do in math is try to find ways to be strategically lazy. In other words, instead of showing that six things are the same in order to say that they're the same triangle in terms of size and shape, we're going to try to be more efficient, which is another way to say strategically lazy. And see if we can find ways to show two triangles are congruent with less stuff.
Is that what we're doing today?
That is.
Oh, that sounds great and fun.
Okay.
Ooh, it's a
Um,
postulate. I remember those. Those are things we're supposed to just accept when not question.
um, I think that's going a little bit far. It's always healthy to question things. I think that maybe accept because we can't mathematically show this has to be true. But we also, it has not ever been shown that we can find a counterexample, one that proves this wrong. And
Got
that's
it.
kind of where we're at. Okay, and this is talking about that we call this side, side, side. We're going to use S and A a lot in here because we're talking about sides and angles. And SSS, side, 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 uh, is telling us that if all three sides of one triangle are congruent to their corresponding sides of a second triangle, that means that those two triangles have to be congruent.
So is this saying if I had like a set of 3 sticks,
Hmm.
and then I had a set of 3 sticks that were the same length as those 3 sticks,
Hmm.
I could only make one triangle?
It is. That's exactly what this is saying, and that's actually the really important part of this, because we're going to get into kind of the mathematical weeds here of we're proving triangles congruent for the sake of proving triangles congruent. But the big deal here is that if I have three side lengths, there's only one triangle that I could possibly build with those three side lengths. It might be flipped, it might be rotated, it might be translated. I should have said reflected instead of flipped, so I kept all three in the transformation thing. Um, but there aren't different triangles we can make with that.
And that would be an activity we might do if we were in class and this were
Hmm.
normal life, where we
It's
give
true.
you 3 sticks and 3 sticks, and those sticks are the same, and you try to make different triangles.
It's true. That is an activity that I have done many a time in yesteryear.
So here we're going to show that these two triangles are congruent using that side, side, side. So our only job is to get 3 sides. Once we've gotten 3 sides are congruent, then our life is a little bit better. So we already are given one. So we got LM is congruent to NP. And then we've got LP is congruent to NM.
One
So
of the
we need a third side. Go ahead.
one of the things that I like to think about is kind of the beginning and the end of this at the same time. So if we know that our goal is LMN is congruent to NPL, uh, and we're told that we're potentially using SSS here, we can work backwards too. There's kind of a cool thing that we can look at here, and there's going to be something that's pretty obvious for us to see the more often that we use it. But if we know LM and NP, okay, that's there and there. We know LP and NM, so that's there and there. The missing pieces are going to be tying L and N together and N and L together. Because if these things are congruent triangles, their corresponding parts have to match up in that order.
So you're saying I should just basically write that.
That's not a bad idea. In fact, I hadn't even thought about doing that as a method until I started talking and looking at those letters down below. Because the other thing that we see in the diagram, we talked about this in the last video, is that the only side that's left to talk about is the side that's shared by both of these triangles. And that happens to be Ln. And either talking about this as identity or reflexive property, or if you say it's congruent to itself, any of those things would basically say that this gives us our third side. So now we have side, side, side. And because of that, we can say that this is a pair of congruent triangles. Just to kind of summarize, we stated the two things that were given to us. We kind of organized ourselves a little bit. We wrote the stuff down at the end that we knew we were going to, and we kind of worked towards the middle to make some sense of that. All right.
This is just introducing some vocabulary, talking about an included angle and an included side, which will be over here. So you can show relationships between a pair of corresponding sides and an included angle. So the included angle is in between, say, side AB and side AC. So it's right in between there, squished in between there. And then same idea for an included side. The included side is right between angle B and angle C, and that will come up in two of our triangle congruences.
Oh, look, it's another postulate.
And this has an included angle.
So we said the last one was the SSS because it's side, side, side. This is SAS because it's side, angle, side. One of the things that I find really helpful with this is to label triangles with side and angle. So I'm going to call this side and then an angle that we know something about and then a side that we know something about. I chose to label those three because that's where things are marked being congruent. And if I do that and then I read those letters, that's side, angle, side, that helps me kind of see that included angle thing. Sometimes it's really hard for students to see that. And I find that a little bit easier.
When you said side angle side going that way, could I have gone this way? Side angle?
We could not because we have this gap in the middle.
Oh, so have to go by like the pieces that we actually have.
Yeah. So sometimes you're going to have more information than you need, and you might be able to build some different things with that. But we're going to talk about ones that work and one that doesn't at some point. Maybe I don't know if that's today or not.
So in this one, this is as if I give you two sticks.
Yep.
That are screwed together at some specific angle. And you have to try to make a triangle, and there's only one triangle you can make.
Yeah, so if I wanted to connect those two endpoints, there's only one way to do that. It's not like I can have two different lengths that will actually match that. So that's why this one works. That's why this is a postulate. So this is not what we would call a rigorous proof, which involves math stuff. This is something that we can talk about, understanding that if I set something up like this, I can't make a different triangle there. There's only one I can build. All right, what other information do we need? Okay, I'm going to start at the top this time. I like that because you already started at the bottom. So we're given EF is congruent to DG. So I'm going to call those sides so we can have some stuff. I see that same thing I saw in the last example where we have this segment that's included in both triangles, that DF, and I'm going to write that down. I figured that might be useful. So DF is congruent to itself. I'm going to write that as DF or FD. I'm going to write that as FD because it helps with the letter stuff down below a little bit. And we said that was either by identity or by reflexive. Okay.
So you have a side, and then you have another side.
Well, if we knew that third side, we'd have SSS. But I feel like we're not supposed to use SSS because you wrote SAS there.
That's because up top it says use
Oh,
SAS.
not just a Swiss airline.
That's
Um,
true.
okay, so if we want SAS, and we're talking about, for example, in triangle EFD, this top side and then this diagonal side, we need the A to go between them. So I can't use this angle down here because that would not go between them.
Which angle is that?
Angle EDF.
Okay.
I can't use angle FED because that's not between those two sides. So to me, it looks like I have to use angle EFD because that would be between the two sides up top.
Do you
Um,
also then have to use angle GDF?
because that would be between this bottom and this middle side. That would
Yeah.
make sense to me. So this we'd have SAS and SAS, and that would work for us.
So if we were finishing our little kind of statements here, we've got that, we've got that. So we also need angle EFD is congruent to angle FDG.
Right. And since this question is asking what we would need to be able to say that these were congruent, that's the information that we would need.
And we could connect this to previous information. If
I
we
was
were
just thinking that.
if we were told that these two lines were parallel,
Oh, and then this would be the transversal.
then we have alternate interior angles.
And since we know that alternate interior angles are congruent, therefore those two angles are congruent. I like it.
Right. That's where my brain went. I don't know if that's where your brain went.
It is exactly where my brain went, which is nice. And we even like finished each other's sentences there. That was a great page.
It was. We did great.
All
Feel like we should
right.
start singing. So it looks like we have, if I go with your labeling idea, a side, an angle, and a side, and a side, an angle, and a side. So is that just side, angle, side?
It is.
Okay.
So I'd say yes, because we know that that one works for now. B, I'm looking at the same thing. I've got a side, an angle, and then a side, and then a side. Oh, an angle, and then a side. But those don't go in the same order.
Is that a problem?
This one, if I go kind of around the triangle, I've got SAS. And here, if I go around the triangle, I've got SSA. If I don't, like, there's a big gap here, so I can't go over that big gap. Those aren't the same order of stuff.
Is it fair to say when you're saying big gap, the big gap is if you're skipping two or more pieces? So like an
I
angle
think
and a
so.
side? Okay.
Because here we're skipping an angle, but it's like side and then another side that's right next to it.
Got it.
So this one, I'm going to say a giant nope.
Like Leslie. So this next one, we've got S, 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 and S, S, S.
Hey, that's one of the ones we got.
So that's side, side, side.
Okay, so for the next one, I've got S and then S and then S, and then I've got S, S, S again, which also works.
I wanna jump on this one for a minute here.
I figured you might.
If I name this triangle, I want to write which two triangles are congruent.
Ooh, that's fun.
Because the order here, you have to be a little bit careful.
It's true.
Because of the way they've marked it. So I'm going to write TO matches up with FO.
And that's because you're going from the point that's between the three marked and the one marked.
Yeah.
To the center in both of those.
Yeah, I'm thinking that as I go along the one mark.
Yep.
Yeah.
And
from
the
3 to 2. Yeah.
Yeah.
And then so I did TO. So then there's OR is congruent to OE, and that would be the correct way to write it. So you just have to be careful how you're going to write. That's called a congruence statement. You have to be careful the order in which you write those letters.
I wanted to jump on something else for this one as well. I want to erase stuff first. That if the first thing that you noticed is that these are vertical angles, this one could also be SAS, because we would have a side, then an angle, then a side, and that would be okay as well.
So you're saying they didn't even need to give us TR and EF being congruent?
Correct. Cool.
So this one's saying the same thing. We want to prove triangles congruent with how to show all the pieces are. This one, if you look at this sticky note here, if I make it bigger, if I click on it correctly and make it bigger, we've already talked about SSS and SAS. So here we're going to talk about ASA and AAS. Just as a note, this will not show up, nor will the backwards version of that. So don't write that. It's not a congruence that works.
And if you're really curious, it's because there's more than one triangle that you can build with those pieces.
Which, if you talk ever about the law of sines, you would see that, because that is a case in something of the law of sines. You don't know what that means yet, but maybe someday.
All right, so here we have an angle side angle, the ASA. That reminds me a lot of the SAS, because we've got like an included piece in this. And here we've got an angle.
And that was that picture we had earlier.
Oh, and then the side between them. Oh, it's like we referenced that and now we're talking about that. That's cool.
Yes.
Okay, let's see what they ask us to do with that. Oh, so they're asking us which ones work with ASA. So we did this with SSA and SAS. Let's take a look. I have an issue with this problem. I think Mr. Butterworth knows the issue I have with this problem. Oh no, I don't. Never mind. I misread this problem. I thought it was asking us which ones we could talk about with ASA, but it's asking specifically about these three triangles.
Yes.
Cool, we're good.
I have an issue with how they're lettered, but we'll get there later. So when I look at this, I see that I have an angle, a side, and an angle. I have an angle, and a side, and then I have an angle, a side, and an angle. So pretty quickly, I should be able to see this one does not work, because I didn't have the side in between the two angles.
Okay.
So that means that those two triangles are congruent. So now I have to write them, and I have to make sure I pay attention to the order. Now, I'm going to go with angle marks. So I'm going to go with the one angle mark, and then the two angle mark. I'm going to do the same thing in the other triangle. One angle mark, two angle marks, and then I'll write the last letters. So no angle marks and no angle marks. So the issue I mentioned with the lettering is I would have liked that to say hog is congruent to cat, because that's what the words say.
Yep,
But
and
it doesn't
that's
say that.
definitely an important characteristic to think about.
Yes, hogs and cats are obviously the same. But they might have done that to try to trick us that we wanted to write hog and cat.
Interesting.
But that hog and cat are not the correct order of things.
The reason that I don't like this problem is because these three triangles actually have another relationship, because we know something about if two angles of a triangle are congruent to two angles of another triangle, then the third angle has to be equal as well, because they have to add up to 180.
Oh, so you're saying that the third, if I get rid of this blue stuff I drew, the third angles have to be the same. So we have angle O is congruent to angle F, which is congruent to angle T.
Yeah, and the fact that this was kind of used to make this, it makes me uncomfortable, because that makes it feel like this could be the case. The problem is that this side doesn't match up between the right angles as this side does. An example of this that's would be a little bit easier for us to see is if we had two triangles, and I'm trying to draw pretty specific triangles for us to see, that these angles could be congruent, but it's like the longest side and not the longest side that appear to be congruent in these ones. We have a name for these that we're going to come back to. These are called similar triangles. You've used that word in previous courses, so I don't mind kind of giving that away. But this is a little bit weird about ASA, and then are we doing AAS next?
Yes.
Yeah, it's
I think the intent behind the problem is to make it clear that the side has to be between the two angles.
Yeah.
And I think that's their goal. If we added an additional piece to this question that said, could these could triangles, the two triangles on the left, could those be congruent sometimes, always, or never? That could be an interesting discussion to have, where they could be congruent because we don't know the angle measures.
Yep, I think that's fair. Angle measures would not play into that. Side measures.
No, if so, the side measures,
because the angle measures for all three of these are equal, no matter what.
Right, but I mean, if angles 2 and 3 are the same.
Oh, sure. Yep.
Then those triangles could be congruent by.
But that involves some more stuff we don't know yet.
Yes. And the kids were just like, "What are you talking about?" Okay, so this is a theorem. A theorem.
Ooh.
So that's different. Is that because of what we were just talking about?
Yeah. So this is
have the two angles. We know the third angles.
This is only a theorem because we said that the previous page one was a postulate. We could also go the opposite direction. It doesn't matter as long. Yeah. Math is annoying sometimes.
So we don't really care whether they say theorem or postulate.
Not for these, because all these are really arbitrarily named, to be honest. Same with all the parallel line stuff, but I'm not going to reopen that can of worms. So the key part here is we have angle, angle, side, where we don't have the side in between. Notice that it goes angle, and then side. Right.
Angle, and side. So the side is not between the two angles.
And that's what we saw in the last page for the one that didn't match up. But in this case, both of these have that order. And the reason that this works, if we accept the previous one is true, is by that reason that this third angle must be congruent as well. Therefore, we could say this is angle, side, angle if we show that first.
Got it. So we're going to do a little proof here of the angle, angle, side theorem. We want to show that triangle ABC is congruent to triangle DEF. We're given an angle, and a side. So we got AC is congruent to AC. No, DF. So we're given an angle, and a side. That's all given information.
Okay, I also know that within a triangle, the angles have to add up to 180. So we can talk about this that way. We can also use that third angle theorem and write less stuff. I don't know how you feel, Mr. Butterworth, about either one of those options.
I mean, I think I would just say, okay, we know C has to be the same as F.
Yep.
Because of angles of triangle equal 180 or something like that.
Sure.
And I would just put that. And that would allow us to, we'll add a third piece to these, C and F. And then we have the angle, side, angle idea.
Yeah.
And so then we can show using, let's see, we want to use angles, that one, and that. And that's by angle, side, angle. So we used what they said was a postulate. We used that to prove that this theorem is true, because we didn't use the B and E congruence to directly show that the triangles are congruent. We used the B and E congruence to show that C and F had to be the same, and then use angle, side, angle.
So because this works when we were given this information, this one has to work also.
Yes.
I don't know if you can actually see that or if our pictures take up that space, but that says AAS in the top corner.
I can see it.
Excellent.
Our pictures are to the side. So this is something that you guys should do right now. So you should pause the video. I'll also put in some questions, but this you should be able to come up with some answers for. So pause the video and then we will write down the answers.
Okay, nice pausing. When I look at number 1, the first thing I want to do is to draw that triangle. Is that weird?
No.
I feel like drawing things is super helpful. And then if I'm looking for between angle R and angle S, to me that looks like that side there. So that's going to be RS.
Love it. Should we do the same thing for triangle nom?
I love that idea. Nom nom nom.
So we just draw some triangle, and does it matter what the triangle looks like?
It doesn't.
We kind of drew similar triangles, like similar looking triangles.
Yeah, I think that just because our default is to draw triangles that tend to be equilateral-ish looking, just because we end up drawing that with our hands.
Got it. So NO is included between which angles? So that's saying which angles are on the outside of that. So that's O and N.
So if I were to draw this triangle this way, which is clearly different, we end up with the same thing. And you know what? I'm even going to mess that up even more. I'm going to change the order of the letters.
Whoa.
So we got N-O-M, and we want N-O. Okay, that's between O and N. Hey, same thing.
That's what I said. And I think I already answered the bottom ones by labeling. So I labeled the bottom ones simply based on the information we had. And you should be able to see that we have angle, side, angle for the first one. And then angle, angle, side for the second one.
Cool.
And the last thing, talking about isosceles triangle. So isosceles triangle, we'll go with the definition of at least two sides of the triangle are congruent. So here we're told AC and BC are the same. And then the claim is that A and B, the angles are the same. So
by the way, sometimes we call these base angles.
We do. Or bangles if you want to walk like an Egyptian. I'm a little confused by the picture below because that 54 is floating in space.
Yeah, is that meant to be here?
Is right there is where 54. Oh, that's interesting. I went the other direction.
Well, because they're both, those are marked as congruent already.
Oh, okay. So you're saying 54 is going to be the piece that you said.
Yeah, because then we can, based on this theorem, we can say this is 54 as well. You can use that to figure out the whole thing. And then since those are equal, cut it in half.
Oh, I see. So if this is 54, that's 108 total.
Yeah, so there's 72 for the measure of angle ABC left over.
So that's that whole angle. So then each piece is 36.
Yes.
Got it.
I'd like to, I know we are out of slides in terms of stuff. I'd like to spend a second talking about this theorem for a second. Are we okay with that? I
am great with that.
I didn't know if that was something that we talk about in a later thing or not. We may. But if we have an isosceles triangle, I'm going to use the minimum of 2 equal pieces. One of the things that we can do is add, we've used auxiliary lines before, and I'm going to add one to this triangle.
Does auxiliary just mean like extra lines that we're drawing in?
It does, and we can give them whatever characteristics that we'd like. In this case, I'm going to use the auxiliary line that sort of is here and say that this auxiliary line is bisecting that top angle. So we also have this middle piece, and since that's in both triangles, sorry, I accidentally switched to eraser, that has to be congruent to itself. So by side, angle, side, these two halves have to be congruent to each other. And separating those.
So if I think of that as distinct triangles, you're basically showing this.
Exactly. And we know by what congruence means. That means all sides and all angles have to be congruent to their corresponding pairs. So if we are looking at this triangle and this one, those angles would correspond. Therefore, those angles would have to be congruent as well. That's this base angle thing, which is often called the base angle theorem instead of the Isosceles Triangle theorem. But again, math is a mess. We name things differently.
Now, in terms of this, now that you've done this, the green one dotted ones that you're saying are the same. Wouldn't these ones also be the same?
They are.
And then if I use the stuff we've done before in this class, they're next to each other. That's a linear pair.
Mm-hmm.
So they're
So
congruent. They add up to 180. So that means they both have to be 90.
yeah, so those have to be right angles. That's kind of cool. And there's one other thing is that these bottom sides would have to be congruent as well. So not only is this what we would call an altitude drawn from the vertex to the opposite side and perpendicular, or the height of this triangle, but this would also be something we've talked about before because it's cutting the bottom into two equal pieces. It's bisecting it. So this auxiliary line that we drew bisects the top angle, it bisects the base, and it's perpendicular to the base. So we can often call this a perpendicular bisector.
There's a lot going on with that altitude you drew in.
Yeah, there's definitely a lot. Isosceles triangles are neat.
Cool. I think we done
Cool
did it.
indeed.